Mathematical induction. This is a method of mathematical proof that we'll be making use of a couple of times in our journey toward the Basel problem. So the best way to really get a handle on this is to work an example. We're going to demonstrate it. All right, so it's called mathematical induction. Well, let's just write that down up here. Mathematical induction. All right. So what we're gonna use is a theorem that you've seen before. In fact, we touched on it briefly in the last video. We're going to take the sum of the numbers from 1, k equals 1, to n, some number n. Okay, so of the sum of the first n digits, actually, or the first n positive integers. And so that expands out to 1 plus 2 plus 3 plus ... plus. And then the last couple in this whole list would be n minus 1 plus n. So that's what this means. We're looking at the sum of the first n integers, n positive integers. And you may have seen this before. That we can use this formula rather than summing up a whole bunch of stuff. Hey, we can use this formula to save ourselves a fair bit of work, especially if n is large. So if I want to, if I want to sum up the first, say 100 positive integers, and we got 1 plus 2 plus 3 all the way up to 100, we can simplify our lives really easily by taking 100, multiplying that by its successor, that's the number after it, 101. And what do we get? That's all going to work out to, what is it? Well, let's do it in a couple of steps here. Hey? Okay, so that's 101, with a couple of zeros after it. So that ends up being 5,050. And we could do a bunch more of these, okay? But even no matter how many we do and we get it works for, we haven't tried all the numbers, right? So we need to bypass that. So what we'll do here is let's erase this. Okay, let's get rid of this. And up here, and let's use a different color just so that it kind of stands out. There we go. We'll use a different color. And let's try this right at the beginning of the number line for n equals 1. Okay, so if n equals 1, then what we're talking about is the sum of the first one digit. Okay, what's that going to be? Well, let's figure that out. Okay, so we'll plug that into this formula here. We get 1/2 of 1 times the successor of 1, which is 1 plus 1. We better work that out. Oh, that's 2. Okay, and that all equals, so 2 times 1, but it's a half, equals 1. Okay, so look at that. We've worked that out using this handy dandy formula. The sum of the first one digit is 1. Okay, I mean, that's what we would call a trivial result, which is math talk for like duh. Okay, we haven't really discovered anything exciting here. Okay, but now what we're going to do is we are going to assume, I know it's starting to sound bad because we're making assumptions, but really what we assume and then follow that assumption through on its implications. So what we're going to assume is that this theorem here, this formula works for some number k. We won't even say at this point what k is going to be. Okay, just some number k. All right, so we're going to write this all out again, and let's choose green here for that, working that out. So what we're saying, and really it's just going to be a repeat of what we've got up here, the sum of the digits, and actually instead of k, we're going to use p because we're already using k. So the first p digits, I should say the first p integers, okay, 1 plus 2 plus 3 plus etc 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 plus, and then the last couple here leading up to it, plus p minus 1 plus p. I mean, if this is true, then this will work for the number p, whatever that is. All right. So again, I mean, we haven't proven anything. We're just making an assumption. Okay. And so now let's follow through with this assumption and see where it takes us. Okay. So if this is the case, okay, then that means that the number following p, okay, which is p plus 1, okay, it's one more than p, right? Okay, it's going to be equal to 1 plus 2 plus 3. I mean, this is just the definition. I'm just expanding out this sigma notation. Plus p minus 1 plus p plus p plus 1. Right? I mean, we just added p plus 1. And now we got all of the digits from 1 to p plus 1. So, I mean, this is the definition of what we're doing. Okay, but now if this thing here that we assumed, if that's true, then I mean we've already seen this bit right here, haven't we? From let me change my color here so I can really emphasize this. We see this here. Well, I mean that's the same thing here, isn't it? That's exactly what we've got here. Okay, that's our first sum of the first p digits. And what did we assume that was? We assumed that that's this. So let's write this down. 1/2 p times p plus 1. Okay, that's what this part is. Okay, and then we'll go back to, let's do blue. We'll go to blue. I don't know all these colors. Plus p plus 1. Okay, that's what this is. That's what this all works out to. Okay, and I've just split it up now into these two bits. Now let's put all this together. So I'm going to take 1/2, and you know all of this here, all of this business here. Let's put it all in brackets. Okay, so I'm just going to carry this into the parentheses, or I should say the brackets. All right, but now when I pull this into the brackets, I'm going to need to take into account this half. So I need to double everything. So plus 2p plus 2. Alrighty. And now let's sort this out a little bit more. We got 1/2. We better do some expanding. P squared plus p plus 2p plus 2. And now we can combine these two terms right here. So that equals 1/2 of p squared plus 3p plus 2, and we'd better put all that in parentheses because it's all getting halved. And now we've run out of precious real estate, so we're going to need to squeeze all this stuff up into a corner here. Okay, so we've tightened things up here, and we're down here working with this, with, well, what turns out to be a quadratic. So let's just continue on with that. So we're going to factor this equals 1/2 p plus 1 times p plus 2. All right. So now what have we got? Well, we've got that an assumption that this formula works for some number p. Okay, we haven't proven anything, but we've shown that if it works for some number p, then p plus 1 will look like this. But what is this if not the same formula except with p plus 1 in the place of p? Here we've got the sum of the first p integers is given by 1/2 of p plus the number following p. Okay. And here we've got the sum of the first p plus 1 integers is given by 1/2 p plus 1 plus the number following p plus 1. Okay? So if the formula works, again, we haven't proven yet that it works for any number, but if it works for some number p, guaranteed it will work for the number after p. Okay, so now all we need to do is find a number p, right? Well, we did that right here at the beginning, didn't we? With this trivial duh result. Okay, we know that it works for n equals 1. Okay, so by this argument here, okay, we know that it also works for n equals 2. Okay, but since it works for n equals 2, it also works for n equals 3. And since it works for n equals 3, I think you get the pattern. So we've shown that this property is true for n equals 1. And so by induction, like an electric current, it goes all the way through the number line. Okay, all of the positive integers catch this property. So now we've demonstrated it for any number n, in fact. So we want to summarize that using the sigma notation. Okay, what we did here, we'll go back to this color. What we did here is we showed that sigma, the sum of the k equals 1 to p, okay, and all of these equals 1/2 of p times p plus 1. And we've shown that if this is true, then that implies, that's what this arrow means here, fancy arrow that I've drawn. It means that this implies that the following is true. So here's a more of a semi-formal way of writing this down. 1/2 p plus 1 p plus 2. Okay, and we got that by just following through with the implications. Okay, so we showed that the one implies the other, and then we went back to the very beginning and showed, okay, but it's true for p equals 1. Okay, true for p equals 1. So therefore, it's true for 2, 3, 4, all the way up to infinity and beyond. Okay? That is a demonstration of the proof by induction. Proof by induction. As always, like, comment, share, subscribe, do that kind of stuff, and we'll see you next time.